What's up, everyone? Welcome to Axiom. If you've been studying general and circular queues still confuses you, don't worry. By the end of this video, you'll have a crystal clear understanding. Let's jump in. Low-level programming treats strict memory management as a structural requirement. In these environments, inefficient memory handling leads to systemic failure. The queue data structure maintains order through the first in, first out FIFO principle. The first item inserted into the buffer is the first item taken out. A standard linear array implementation relies on two integer variables to track data. We start with a 6-block array, numbered 0 through 5, with the front and rear pointers initialized at -1. When we perform an in-queue operation to add an element, the rear pointer steps forward one index at a time. Because the system only increments an integer, this insertion happens in O of one constant time, meeting the primary requirement for algorithmic efficiency. Deleting an element through a dequeue operation steps the front pointer forward to the next index. This deletion also occurs in O of one time, because the underlying data remains in place. The system simply updates the pointer. While this speed is ideal, the forward march of both pointers eventually consumes the entire array. This creates a spatial footprint that cannot be sustained over long-term runtimes. This creates a conflict in the system's logic. We have a new element with a value of 100 that needs to enter the queue, and there are visibly two empty slots at the front of the array. The system fails to utilize this space because the algorithm only checks if the rear pointer has reached the maximum size of the array -1. The algorithm evaluates this condition based purely on the rear pointer's location at index 5. It ignores the empty space behind the front pointer. The condition evaluates to true, and the insertion is blocked. Shifting the remaining elements to the left to make room would solve the space issue, but it requires an operation that sacrifices our constant time performance. This flaw is known as pointer drift. Constant time operations have stranded perfectly usable memory. Without a way to reclaim this stranded memory while maintaining O1 speed, standard linear queues are ineffective for continuous systems. The ring buffer, or circular queue, provides a conceptual solution to pointer drift. This model aims to connect the final memory index directly back to index 0. However, physical RAM is strictly linear. Computer memory architecture contains no actual circles. Circularity is an algorithmic abstraction. In reality, the data sits on a rigid, one-dimensional line. Because we cannot change the physical shape of the array, we must change the logic of how pointers move through it. We need a mathematical function that allows a pointer to jump from the final index back to index 0 without breaking the sequence. Creating a loop on a straight line requires a transition from basic addition to cyclical mathematics. The modulo operator provides the structural fix for pointer navigation. The modulo operator calculates the remainder of an integer division. In memory architecture, this remainder serves as a strict boundary enforcer. When a value on the left is smaller than the boundary on the right, such as 4 modulo 5, the equation returns the original number. In these instances, the logic functions like basic addition. The critical change occurs when the pointer value reaches the boundary value. When the boundary is hit, the remainder is 0, forcing the output back to the start. For the blocked rear pointer, 5 plus 1 is 6. 6 modulo 6 yields 0, jumping the arrow seamlessly back. Element 100 occupies index 0, reclaiming the stranded memory. Since this calculation occurs instantly, The system preserves the zero of one-time complexity requirement. The modulo arithmetic converts a one-dimensional line into a closed loop, resulting in a continuously recycling memory buffer. This circularity introduces a new question. If both pointers wrap around the array indefinitely, how do we prove the queue is full or empty? A front pointer value of -1 defines the baseline empty state, indicating that no data has been tracked. There is also a specific reset condition. If a dequeue operation causes the front pointer to equal the rear pointer, the last item has been removed from a buffer. Upon this collision, the algorithm manually resets both the front and rear pointers to -1. Defining the full state requires more than just checking the end of the array. In a circular queue, a full state occurs when the rear pointer wraps around and catches up to the front pointer from behind. The formula for this check is rear plus 1, modulo max size equals front. If the predictive modulo step for the rear pointer lands on the index currently occupied by the front pointer, the insertion is blocked. Unlike the false overflow in Act 1, this state confirms that 100% of the memory capacity is utilized. The reliability of a circular queue depends on accurately defining these pointer collision states to ensure data is not overwritten and empty space is utilized. A ring buffer can be implemented using structures other than arrays, such as a circular linked list. This comparison shows the two methods. While the array uses modulo math, the linked list achieves circularity through a curved pointer connecting the tail node to the head node. The linked list approach is often easier to conceptualize because it bypasses mathematical operations in favor of direct node links. However, the array implementation is frequently favored in technical environments for its efficiency. Linked lists require dynamic memory allocation, which forces the system to request fresh heap memory for every new node at runtime. The array implementation avoids this by reserving a fixed block of memory at the start and recycling it without further requests to the operating system. For mission-critical systems where dynamic allocation is a liability, the array-backed modulo-driven circular queue provides the required predictability and efficiency. This data structure is a foundational element in modern operating system mechanics. It is a core component of CPU scheduling, where processor time is distributed to a list of processes in a rhythmic repeating sequence. It also facilitates inter-process communication, acting as a safe holding area where different programs can pass data streams without memory leaks. Complex computing environments function reliably because they rely on these specific integer constraints. By replacing a simple plus sign with a modulo operator, developers transform a flawed linear queue into a continuously recycling system. And there you have it. Circular queues simplified. Remember, understanding the basics is key to cracking exams. Hit like if this helped, subscribe to Axiom for daily lectures, and comment below with any doubts. I read every single comment. See you soon.